Hello students, I welcome you to this session. Today we are going to see yet another cycle known as Bell-Coleman cycle. In earlier session we have seen reversed Carnot cycle, whereas reversed Carnot cycle is only theoretical or it is ideal cycle only, and Bell-Coleman cycle is a practical cycle, whereas in practical situations this cycle is most applicable, and we are going to see in detail. Now we see the theory behind this, and if possible we will see the problems in this session, or I will postpone to next session. I will discuss wide variety of problems in this particular cycle. So far we have seen these topics, and now we are going to start Bell-Coleman cycle. It is a completely practical cycle, whereas reversed Carnot cycle is a theoretical cycle. Air refrigerator working on a Bell-Coleman cycle, it is also known as reversed Brayton cycle, or it is also known as Joule cycle. Students, you should not get confused with different names that we are going to see, and remember these names. Whatever name it appear in the exam question paper, you should be clear with that. Whereas when you get reversed Brayton cycle, you should answer only Bell-Coleman cycle. So it is Joule cycle also is another name, whereas reversed Brayton cycle we discuss here. Brayton cycle you could have studied in your earlier semester in the subject thermal engineering. Here we are going to start the Bell-Coleman cycle that is applicable to air refrigeration. A Bell-Coleman air refrigeration machine was developed by Bell-Coleman and Lightfoot by reversing the Joule's air cycle. So here Joule's air cycle is modified, and it was one of the earliest types of refrigerators used in ships carrying frozen meat. This is the diagram. I wanted to show you these two. One is it is open cycle. Open cycle, there is no input to this refrigerator, and whereas here the brine, this is the closed cycle. It is the brine in and brine out, and it was one of the earliest types of refrigerators using in ships carrying frozen meat. And figure A and B shows schematic diagram of such a machine, which consists of a compressor, a cooler, an expander, and a refrigerator. So these are the components, whereas if you see this compressor, it is a rotary type compressor. Normally in earlier days they used rotary type compressors. So here this is the cycle, students. It is here there is no isothermal process, but we have isentropic process. Isentropic process, constant entropy processes like our Carnot cycle, reversed Carnot cycle. The Bell-Coleman cycle, also known as reversed Brayton or Joule cycle, is modification of reversed Carnot cycle. Carnot cycle is applicable when it is practically applied. These curves are obtained. So these are the PV diagram and TS diagrams. The cycle is shown on PV and TS diagram. Figure A and B at the initial state P1, V1, T1, P the pressure, volume and temperature of air respectively. Similarly, we have for point 2, point 3, point 4. So for each point we have P1, V1 and P2, V2 here, P3, V3 here, P4, V4 here. Similarly, P1, S1 here, P2, S2 here, P3, S3 here, P4, S4 here. Similarly, in the entropy diagram, temperature entropy diagram. There are four processes in this cycle, like reversed Carnot cycle, similar processes only. So the first one is isentropic compression. Similarly, here, as we have seen in earlier cycle, reversed Carnot cycle, the 1 to 2 process is isentropic compression process. Here you can see 2 to 3 constant pressure. This pressure, when it is constant, it is known as isobaric process. I will come to that. The cold air from the refrigerator is drawn into the compressor cylinder, where it is compressed isentropically in the compressor as shown by the curve in the PV and TS diagrams. During the compression stroke, both the pressure and temperature increase and the specific volume of air at delivery from the compressor reduces to V1 and V2. So V1 and V2 are getting reduced. Since this is an isentropic compression process, no heat absorbed or rejected by the air. So no heat is absorbed or rejected by the air. So next one is constant pressure cooling process. It is constant pressure cooling process. The warm air from the compressor is now passed into the cooler where it is cooled at a constant pressure P2 equal to P3. So P2 and P3 are same, reducing the temperature from T2 to T3. So from T2 to T3, the pressure is getting reduced. The temperature of cooling water, as shown by the curve 2-3 on PV and TS diagrams. The specific volume also reduces from V2 to V3. We know that heat rejected by the air during constant pressure process per kg of air is given by QR equal to Q2 minus 3 equal to Cp T2 minus T3. So next is isentropic expansion process. The air from the cooler is now drawn into the expander. So this is isentropic expansion from 3 to 4 expander cylinder where it is expanded isentropically from pressure P3 to the refrigerator pressure P4. So from P3 to P4 it is getting dropped and simultaneously the volume is getting increased. So this is marginal increase only. The expansion process is shown by curves 3, 4 on the PV and TS diagrams. The specific volume of air at entry to the refrigerator increases from V3 to V4. We know that during isentropic expansion of air, no heat is absorbed or rejected by the air. So during any isentropic process, no heat exchange takes place. So that is the basic you should remember always. Next is constant pressure expansion. So this is the last process out of 4 processes. The cold air from the expander is now passed to the refrigerator where it is expanded at constant pressure P4 equal to P1. So P1 and P4 are equal, like P2 and P3 are equal. The temperature of air increases from T4 to T1. This process is shown by curves 4 to 1 on the PV diagram and TS diagrams. Due to heat from the refrigerator, the specific volume of the air changes from V4 to V1. We know that the heat absorbed by the air or heat extracted from the refrigerator or the refrigerating effect produced during constant pressure expansion per kg of air is QA equal to Q4 minus 1 into equal to Cp, that is T1 minus T4. Work done during this cycle is it is work done heat rejected minus heat absorbed. In terms of Q, it is QR minus QA, Cp T2 minus T3 minus Cp T1 minus T4. So this is QR is equal to Cp T2 minus T3, QA is Cp T1 minus T4. So with this formula, we can calculate the work done in terms of Q or in terms of Cp and temperatures. So coefficient of performance is very important. When you see the coefficient of performance and compare to reversed Carnot cycle, the coefficient of performance for this particular cycle is lesser because it is a practical cycle. COP, heat absorbed by work done, as we know it is the basic from right from beginning of this unit. We are discussing this formula, heat absorbed by work done, QA by QR minus QA. In terms of Cp T1 minus T4, Cp T2 minus T3 minus Cp T1 minus T4. So all Cp is getting cancelled and T1 minus T4, T2 minus T3, T1 minus T4. So with this formula we can calculate COP. Or we can have in terms of this also we can reduce it to T4 T1 minus T1 by T4 minus 1, T2 by T3 minus 1. So like this also we can extract. So isentropic compression and expansion relations. For the isentropic compression process, it is 1 to 2 in a PV diagram as well as in a TS diagram. T2 by T1 equal to P2 by P1, that is to the power gamma minus 1 divided by gamma. So for the isentropic expansion process 3 to 4, see in terms of P3 by P4, it is T3 by T4. So isentropic processes we have 1 to 2 and 3 to 4. So P3 by P4 gamma minus 1 by gamma. So since P2 equal to P3, P1 equal to P4, therefore the above equation can be reduced to T2 by T1 equal to T3 by T4, or we can also write like this, T2 by T3 equal to T1 by T4. So please remember this equation, and also this equation we can calculate COP and the expansion, the isentropic expansion process. This relation is very handy. So while solving problems, we are going to see that in next session. So substituting these values in COP equation, here T4 divided by T3 minus T4, 1 by T3 by T4 minus 1. In terms of gamma, so we are substituting here in a denominator. So final COP is 1 by RP. In terms of RP, we can measure this. So RP is the either expansion ratio or compression ratio. It is P2 by P1 equal to P3 by P4. So RP is the compression or expansion ratio. Please remember this RP also. This term we have not come across in the earlier cycle. It is a very important parameter while solving the problems. Please remember this. So work done in the cycle, sometimes the compression and expansion processes takes place according to the polytropic process. In such a case, the COP is obtained from fundamental thermodynamic relations. So work done by compressor during 1 to 2, that is isentropic compression process, per kg of air equal to N by N minus 1. So P2 V2 minus P1 V1 equal to, in terms of R, T2 by minus T1, so PV equal to RT. So we are replacing this. It is the very fundamental equation in thermodynamics. You could have come across this equation in your thermal engineering subject. Work done by the expander during process 3, 4. So we are going to do our relations. We are going to compute most of the problems with these two cycles, with these two curves, especially that is isentropic expansion, isentropic compression. So this is isentropic expansion process, 3 to 4 per kg of air. This is equal to, in terms of same n divided by n minus 1 P3 V3 minus P4 V4. So n divided by n minus 1 in terms of RT. So this also can be computed. Net work done during the cycle per kg of air. So remember this equation is very helpful. So this is WC minus WE. So during compression, during expansion, so W minus WC minus WE, that gives net work done. So net work done. So by combining these two equations, we have this, right? So n minus 1 R T2 minus T1 minus T3 minus T4. So this relation is very helpful while solving the problems. Heat absorbed and COP calculation. So I will give you more relations, and this will be very useful while solving problems, and remember these equations. So here we also know that heat absorbed during constant pressure expansion process 4-1. So 4-1 is constant pressure expansion process. QA equal to Cp T1 minus T4. So COP equal to heat absorbed by work done. So QA by W. So this is in terms of N and RT Cp. This can be written like this: Cp equal to Cp T1 minus T4 divided by N minus 1 or T2 minus T1 minus T3 minus T4. So here this way you can calculate. And we can still simplify this. R equal to Cp minus Cv equal to Cv gamma minus 1. Substituting this into the COP equation, COP equal to, in terms of gamma, we can rewritten this equation here, and this can be simplified further. So Cp by Cv equal to gamma, and we can further reduce to this equation. So this is the final simplified equation we can use in our computations. So coming to temperature relations, in the case of, in this case, the values T2 and T4 are to be obtained from the following equations. So T2 divided by T1 equal to P2 by P1 n minus 1 by n, T3 by T4 equal to P3 by P4 n minus 1 by 1 by n. So n minus 1 by n is for both, is used as power to this P equation. And isentropic compression or expansion, for isentropic compression or expansion, n equal to gamma. So this is adiabatic expansion ratio. Therefore, the COP obtained may be written as COP equal to T1 minus T4, T2 minus T3 minus T1 minus T4. So this is the denominator, T1 minus T4 is the numerator. It is same as earlier case. So a closed cycle or dense air's Bell-Coleman refrigerator here, the main drawback of open cycle air refrigerator is the freezing of moisture in the air during the expansion stroke, which is liable to choke up the valves. Due to this reason, a closed cycle or dense air Bell-Coleman refrigerator is used. In this case, the cold air does not come in direct contact with the refrigerator. So that is the very good advantage in closed cycle. The cold air is passed through pipes where it absorbs heat from the brine, and this cooled brine is circulated in the refrigerated space. So this is the another closed cycle, as I have shown in the front slide there. In the diagram, right, you can see in closed cycle we have a brine coming inside the refrigerator space. The term dense air system is derived from the fact that the suction to the compressor is at a higher pressure than the open cycle system, which operates at atmospheric pressure. So this is the dense air system, and it has its advantages over open air cycle system, and a closed cycle also having the all the relations which are also good. Here you can apply all those relations to compute COP and other parameters. There ends this theory. In next session, students, we are going to start the problems. Let us discuss problems, wide variety of problems I wanted to discuss, and please practice the problems like mathematics. It will be very useful and very easy. If you practice these problems, there is nothing difficulty in this. You can easily practice the diagram, practice the problems. So I have given you equations. These equations only we are going to use in next session, that is problems. And coming to textbooks, same textbooks, Rajput, and I preferred RS Kurmi over Rajput and CP Arora, and NPTEL courses are there. You can refer those courses. Brighthubengineering.com /HVAC. This also gives you a few preliminary what you call information, preliminary information you can get from this website. I prefer this Kurmi book. It is good, and I will give you all these books, soft copies to you when you come and meet me in our regular sessions. In regular meeting sessions, I will hand over all the books. Please practice problems. Already we have seen a few problems on reversed Carnot cycle. If you practice more number of problems, and I will also post few questionnaire and solve them and submit in either Google Classroom, or you can submit to me in person. So that's all for now, students. Uh, please practice the problems, and I will keep on insist you to practice problems so that you will get good practice, and it will be very easy while solving the problems in the exam. Thank you, students.